get right down to it, all of particle physics is completely fascinating. But generally, each scientist develops expertise about a specific subject so they can then advance humanity's understanding of the laws of nature. At Fermilab, researchers decided that studying the behavior of neutrinos provides the best chance of making a breakthrough. Fermilab is already the flagship accelerator-based neutrino laboratory, and by building the International Deep Underground Neutrino Experiment, we're working hard to stay that way for the next several decades. Neutrinos are fascinating particles, which can change their identity from one form to another. That's pretty crazy sounding and needs some explanation. For instance, if a neutrino were an animal, it would be like a cat turning into a jaguar, then into a tiger, before turning back into a cat again. Studying that morphing behavior of neutrinos is key to making discoveries. But before you can study the identity-changing behavior of neutrinos, you first have to be able to detect neutrinos. And that takes some doing. Why is that? It's because neutrinos don't interact very much. In fact, neutrinos from the sun can pass through the Earth very easily. In very rough numbers, for every 10 trillion neutrinos hitting the surface of the Earth and passing through the thickest part, one of them interacts somewhere in the Earth, and the rest pass through unscathed. Now, our detectors are big, but they aren't as big as the Earth. One of the bigger detectors is a tank of water weighing 50,000 tons. And then there is Fermilab's even more massive dune detector, which, when completed, will have a total mass of nearly 70,000 tons. They're both tiny compared to the Earth, so that means that most neutrinos will pass through detectors, well, undetected. So how do we detect them? Actually, it's extremely easy. To all intents and purposes, neutrinos interact exclusively via the weak force. The weak nuclear force is the weakest of the three known subatomic forces. Gravity is weaker, but it's so much weaker that it's entirely negligible. At the subatomic level, interactions occur when a matter particle emits or absorbs a force-carrying one. For the weak force, there are two force-carrying particles, with the unimaginative names of the W and the Z boson. Both particles are very heavy, just shy of 100 times heavier than a proton. The Z boson is electrically neutral, while the W boson comes in two varieties, one negative and one positive. The way a neutrino interacts is that it is just traveling along, and when it gets near the nucleus of an atom, wham! The neutrino emits either a W or a Z boson. The W or Z boson that was emitted by the neutrino then goes and plows into the nucleus of an atom, breaking it up and creating all sorts of particles. Stray protons and neutrons can come out, but so can other particles that are created from the energy of the collision. It's an E equals mc squared thing. Every collision is different. Sometimes lots of particles come out, sometimes a few. We can predict how often we'll see each kind, but individual collisions are random. However, those particles that come flying out of the destroyed nucleus fly by the atoms in the detector. Depending on the particle detector technology used in an experiment, those secondary interactions make electrical signals or blinks of light that can be detected. There are lots of different technologies employed at Fermilab to detect neutrinos. So that's all there is to it. Neutrinos emit W or Z bosons, and those W or Z bosons break apart atomic nuclei. The debris then smashes into atoms, and those interactions are detected. Easy peasy. Of course, it's possible that you're confused at this point. Scientists make a big deal about how hard it is to detect neutrinos, and yet, I just told you how easy it was. Something clearly isn't adding up. And that's because, while I've answered the question that some viewers asked, perhaps that isn't exactly the right question to ask. The proper question is both, how do we detect neutrinos, and why are neutrinos so hard to detect? To simplify the explanation, I'm not going to distinguish between the W and Z bosons. While they're different in detail, they have two common features. They're both very massive, nearly 100 times heavier than a proton, and they both live for a very short amount of time. Focusing on those similarities and ignoring the differences, we can simply combine them and treat them as a single particle and call it a weak boson. Now, there are a couple ideas from early 20th century physics that matter here. One is Einstein's equation of E equals mc squared, which says that mass is energy and vice versa. The other is the Heisenberg uncertainty principle, which says that for very short periods of time, energy doesn't have to be conserved. Since mass is energy and energy doesn't have to be conserved in fleeting subatomic interactions, that means that weak bosons don't have a single and unique mass. While their favored mass is about 100 times the mass of a proton, you can find them with masses that are larger or smaller. What you're seeing here is the range of masses that a weak boson can have. Here, where the bump is high at 100-ish, is the most common mass. Off to the side a little bit, close to, but a little different from the 100-ish place, are less common. Further away is even less common. But you'll notice that the curve is smooth and ranges all the way down to 0. Thus, it's super duper unlikely, but it's possible to find weak bosons with tiny masses. Now, in neutrino scattering using the Fermilab beam, the energies are generally much, much smaller than this 100-ish number. In fact, they tend to be way down here. And if you're looking at neutrinos from the sun that go through the Earth, they're even closer to 0. So this is key to why the weak force is weak. Weak bosons prefer to have a mass near 100-ish, but the neutrino interactions at Fermilab need to be very small. That means that an interaction caused by the weak force is very, very unlikely. And you can use the Heisenberg uncertainty principle to get some insights into what's going on. In order for a weak boson to exist with a mass so far away from the normal mass, it can only exist for, in round numbers, for 1/10,000th of a trillionth of a trillionth of a second. If you're interested in how far such an unusual weak boson can move, it can travel a distance less than 1/1000th the size of a proton, which is a crazy short distance. And that is key to understanding why neutrinos are so hard to detect. In order for a neutrino to interact in matter, it has to plunge into the center of an atom and essentially get a direct hit on one of the various subatomic particles inside the core of the atom. If it misses just a little bit, there's no interaction. However, on the extremely rare occasion in which there actually is an interaction, the weak boson just jumps out, smashes into the subatomic particle in the center of the nucleus of the atom, and breaks the nucleus apart. That's the easy part. And, like I said, detecting the particles that come out of the collision is really pretty easy, whether we look at blinks of light or electrical signals. In the DUNE experiment, which will be Fermilab's flagship experiment for the next few decades, liquid argon, which is argon that's been chilled to about 300 degrees Fahrenheit below 0, is what will be used to detect the signals. So there you have it. Neutrinos don't interact very often, but when they do, detecting them is very easy. And now, you're a neutrino detection expert. Okay, that was fun. Neutrinos really are crazy particles to work with. Getting them to interact is the hard part. And if you want to learn more about detecting them, there's a link on your screen that tells you more. If you enjoyed learning about this ghostly and elusive particle, be sure to subscribe to the channel and share on social media, because we're always making interesting science videos. And be sure to click on the little bell to make sure that you get notified about every video we release. Otherwise, you'd miss learning about some awesome physics, and that would be a shame, because of course, physics is everything.